Thank you so much, Sarah. It's great to be here. Let me just set up my screen here. Okay, hi everybody. Thanks for joining today. My name is Lucy MacKenzie, and I'm a water resource scientist at BGC. I'm really excited to share our progress on the bank erosion model that our team has been developing over the past few years. To begin, I actually want to acknowledge the entire team. Although I'm the one who's presenting today, the development of this model was a collaborative effort. Our lead programmers, Vincenzo Koya and Jane Wang, have done remarkable work turning the eroders concept into a functioning reality. And the group of eroders, or geomorphologists, includes Brett Eaton, Sarah Davidson, Kathleen Harita, and myself. Bank erosion is essentially the removal of material from channel banks, causing their location to shift over time and ultimately changing the alignment of the channel. Bank erosion happens when the force of water moving through the stream is greater than the resistance of the bank material, or in other words, when the shear stress acting on the bed and banks exceeds the entrainment threshold of the bed and bank material. Most flows only cause minimal erosion along the banks, but when a large flood occurs, the rate of erosion can escalate rapidly. Under high flows, bank erosion can threaten infrastructure and, in extreme cases, put lives at risk. For instance, as shown here, a 2021 flood resulted in significant bank erosion in the Nicola River Valley and other parts of southern BC, destroying highways, impacting other important linear infrastructure, encroaching on residential areas and First Nation reserves, and ultimately isolating thousands of individuals from essential services. Having the tools to predict and mitigate against this type of damage in the future is essential, particularly in light of a changing climate. Although geomorphic considerations haven't always been integrated in flood hazard assessments, there's a growing recognition that bank erosion and other geomorphic processes such as avulsions can be as or even more detrimental than the flood waters overtopping banks. Here I highlight some recent guidelines that emphasize the need to assess bank erosion when mapping floodplains or when constructing and managing infrastructure such as pipelines. Now, while flood mapping benefits from industry standard models like HECRAS, there is a notable gap when it comes to bank erosion modeling. There are very few models that are available to map areas at risk of bank erosion, particularly for the types of river systems that are prone to the greatest changes during flood events. This brings us to an overview of two very general types of bank erosion that exist, which we like to classify as either vanilla ice cream or multi-flavored deluxe waffle cone ice cream. The vanilla type is progressive erosion and meander migration. This process involves the steady, predictable shifting of the river channel and is typically seen in sand or siltbed rivers such as the one shown here. Over years or decades, the river tends to erode at the outside and downstream side of meander bends, creating classic features such as scroll bars across the floodplain. The multi-flavored deluxe waffle cone type is episodic channel widening. This occurs when a river dramatically widens during a single flood event. It alters its course and quickly transforms the landscape. Unlike gradual meander migration, these episodes can result in substantial loss of land and major impacts to infrastructure in a very short period. Here you can see the original channel alignment of the Nicola River in 2015, overlaid onto imagery from after the 2021 flood. It's this episodic channel widening, or this multi-flavored deluxe cone type of bank erosion, that our model aims to predict. Starting with the original channel alignment, can we model the extent of widening that could occur during a given flood event? Episodic bank widening is most typical in higher gradient rivers, such as those with slopes around 2% or higher. In these systems, while some erosion may occur during smaller flood, the majority of the bank erosion actually happens during large flood events. Unlike their lower gradient counterparts, erosion in these high gradient channels can occur anywhere along the channel, including on the inside of bends. Significant bank erosion in these systems is also often accompanied by channel avulsions, which is where a brand new channel is created, such as the one shown here on the inside of the large meander bend. When it comes to modeling bank erosion in these systems, there are many complexities to consider. First, high gradient channels are often found in areas with complex topography. For example, in the cross-section shown here, one side of the channel has a steep bank while the other is much flatter. If the same volume of erosion were to occur on both banks, The lateral extent of erosion would differ between the two. This highlights how topography and channel geometry play a major role in predicting the modeled extent of the lateral erosion. Second, the shape of the flood hydrograph strongly influences erosion. Rainfall-driven floods rise and fall quickly, delivering a short, intense burst of energy that moves sediment rapidly but for a short duration. In contrast, snowmelt floods can build more gradually, sustain peak flows over a longer period, and this allows for prolonged sediment transport. As such, the shape of the hydrograph can result in substantial differences in how much material is transported and how much bank erosion results. Third, the ability of a channel to move sediment once it's eroded, which is known as the sediment transport capacity, is critically tied into modeling bank erosion. For a given flow, it is possible to calculate the maximum erosion distance, which is the change in channel width that is needed to restore that stability. However, this value can be deceiving. In reality, actual erosion is often less, since it depends on how much sediment the river can actually move during the flood. Accurately modeling bank erosion requires understanding the balance between the potential erosion and the river sediment transport capacity. These complexities begin to shed light on why modeling bank erosion requires careful consideration of multiple interacting factors, and why it took numerous scientists with numerous degrees, numerous years to develop the model that I'm about to introduce. I'm going to split the discussion of the bank erosion model into two components, the spatial component and the bank erosion component. For those of you who care about these things, the model itself is written in the R programming language, and for those of you in the audience who do not care, I will end my discussion of code here, but I'm happy to take questions later. Spatial analysis within the model is important, as it's the mean by which we actually take a real river and break it down in a way that we can model bank erosion along its length. The two main inputs to the spatial analysis are the terrain in the form of a digital elevation model and the delineated bank lines of the river. Although the model can ingest predetermined cross-sections, it also has the ability to automatically generate them based on a center line created from the input bank lines, which is a feat that is actually more complex than one would initially presume. Here I show an example plan view of the generated cross-sections along the center line, as well as an example of what one of those cross-sections might look like in profile view at the top right, with the initial bank locations in orange. What is arguably the key component of the spatial analysis is the widen by function, which takes the modeled eroded distance, which I'll discuss in a second, and applies it to the original cross-section, maintaining aspects of the original topography as shown in the profile. With all of the cross-sections eroded, it's then possible to overlay this bank erosion hazard area over the original bank line. But how does the bank erosion actually get modeled? The erosion analysis takes in the cross-sections that were created in the spatial analysis, as well as a number of variables. Without going into too much detail, as you can see, there are a number of constant variables, but there are also a number of stochastic variables. What sets this model apart and makes the results so powerful is that we use a Monte Carlo approach, wherein the model is iterated to produce a distribution of predicted bank erosion extent. Remember this because I'm going to touch on it again. There's two parts to the erosion analysis. First, during the stability assessment, channel hydraulics are estimated, and from that, bank stability is determined for a given flow. As shown in the diagram, the cross-section may remain stable for lower flows, but then become unstable once discharge reaches a given threshold. The erosion assessment comes into play for cross-sections that are found to be unstable. First, the volume of sediment that can be transported by a given discharge is calculated. Next, that volume is converted into an erosion distance based on the topography of the cross-section. When iterated, this component of the model produces a distribution of modeled bank erosion extent. Modeling is a representation of a physical system. That model is only as good as the data that it inputs, the calculations that it makes, and the underlying assumptions that it relies on. A deterministic bank erosion model would take the data that ours does and would tell you that the predicted erosion extent is, say, 10 meters. While that might be right, it's most likely wrong. Our model takes those inputs and produces a distribution of predicted bank erosion extent, represented here through different quantiles of that distribution. It shows us what a most likely scenario might be, as well as what a worst case but possible scenario might be. Embracing uncertainty and using probability allows us to do some pretty cool things. While it allows us to create the regulatory lines on a map, for example, the geomorphic setback shown here in yellow on the floodplain map, it opens up a whole new world of probabilistic estimates. Shown on the right, each segment of the highway has been assessed for the probability of intersection during a 200-year flood. That means for the area highlighted in red, there's a probability of 75% or greater that this section will experience bank erosion during that 200-year flood. We're just at the beginning of unleashing our model on the world of potential problems that it can tackle. Any scientist will tell you that results mean nothing if they can't be communicated. Utilizing the spatial capabilities of the model enhances our ability to convey bank erosion hazard and then to feed that data into risk assessments for numerous different sectors. Building on this, the model can be used to evaluate how climate change and different mitigation strategies may affect infrastructure risk. For example, we can assess the risk to a highway in terms of annualized closure duration. We can compare scenarios such as no erosion protection, widespread low-level protection designed for moderate floods, and more limited but higher level protection designed for large climate change impacted floods. An approach like this allows us to actually quantify the effects of protection strategies on the length and frequency of highway closures. Another innovative application is to use the model to simulate long-term channel migration, helping us to understand how a river system might behave over centuries. Running the model in this way allows us to generate frequency magnitude distributions of bank erosion, which will provide a statistical picture of bank erosion magnitude. Much like frequency magnitude relationships created for flooding, these distributions can further support planning and risk assessment in river corridors. Going forward, we will continue to advance our model by integrating other BGC-developed tools, such as Riverbank AI. And these tools can provide additional data and insights that will help calibrate the model parameters and improve the accuracy of our prediction. So that's it for me, and thanks all for your attention. I look forward to connecting with you, and yeah, have a good one.
Lauren, do we have any time for questions? And does anybody have a question?
I think we could do one if there's a question there, and otherwise, you can feel free to reach out to Lucy with her email there. I'm sure she'd be happy to chat more.